Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. This particular lecture is the first in a sequence of lectures on group actions. Group actions are the way we use groups, and it's also the way we understand groups. In this lecture, we will see the definition, some examples, as well as seeing how group actions give us homomorphisms and just a tad of how we can use them to understand a group. Let me quickly remind you that a group is a non-empty set with one operation, and that operation is closed, is associative, has an identity element, and each element has an inverse. As long as you have any set with an operation that follows these rules, you have a group. A group is an abstract object in that we don't know what the elements are. We also don't even know what the operation is. It's just we know that we have a set, we have an operation, and it has these properties. Our examples that have been subject of previous videos are of the dihedral group of order 2n. Those are symmetries of a regular n-gon. Topologists would call that dn, but group theorists usually call that d2n. D8, for example, is symmetries of a square. Sn, the symmetric group on n letters, those are permutations of n things, and z mod n, z integers modulo n with addition modulo n, and glnf, the general linear group. How we can analyze this abstract object, all the information about a group is in the multiplication table, but that's very inefficient. Much better is to look at structures and subgroup structures, the substructures that are within a group. If you want to understand if a group is abelian or not, instead of that binary question, which mathematicians don't like, replace that with the question, what's the center of the group, which is a subgroup. By understanding subgroups and the substructures, that's another way of understanding it. Yet another way is to see how the group interacts with other objects. And a final way is to study functions on the group. And the subject of this lecture is the interactions with other objects, although we will talk about functions on the group a little bit also. The intuitive idea of a group action is not that difficult. You have a group, you have a set, so you have now two things. That's the only thing that makes this a little bit complicated, is that we used to just have that one set with one operation. Now we've got two things to worry about. We have our group with its own operation, and we have a set. The group acts on the set, G acts on omega, if every element of G permutes the elements of omega. If you take one of the group elements and throw it at the set, those set elements get moved around, they get permuted. But the permutation is not random, it will respect the group multiplication, and we'll make that precise in just a second. The prototypical examples of a group action are things we have already seen. D8 acts on the corners of the square. Every element of D8 is a symmetry of the square, does something to the corners of the square, moves them around, permutes them. Another natural action is the action of a symmetric group on a set with n elements. A symmetric group is all the permutations of those elements, and the action of the symmetric group will be one of the examples that will guide our way forward. Let me give you the formal definition of a group action. You have a group, you have a set, that's what you're given. G acts on omega if every element of the group, the upside A is for all elements of the group G and G, and for all alpha and omega. So you pick a group element and a set element, and then you are able to apply the group element to the set element. You can think of this as sort of a function, but we write it as G dot alpha. G is acting on alpha, and what you get is another element of omega. As I said, G, the group element, is moving the element of the set to some other element. It takes alpha and gives you G dot alpha, which is another set element. But now here's how this action has to preserve the operations of the group or work well with the operations of the group. It has to be that when you throw the identity of the group has an identity at the set, nothing happens. It has to be that E dot alpha is alpha for all alpha in omega. Also, if you take alpha and apply G to it and get G dot alpha, and then apply H and get H dot G dot alpha, you could have taken a shortcut and instead have thrown HG at alpha and found HG dot alpha. So H dot G dot alpha should be the same as HD dot alpha. These are just the only conditions that we need for a group action, and these have to be true for every group elements G and H and every set element. Here, I didn't talk about permutations. I said that the way you want to think about the group action is that every group element is becoming a permutation. That's something we'll have to prove. So if G acts on omega, what you want to think of each G and G as having turned into a function from omega to omega. And how does that work? It takes the element alpha and send it to G dot alpha. And each of these functions function is going to be a permutation, although that's not a part of the definition. So we'll have to prove that each function will actually be a permutation of omega. The way you want to think about it is that instead of g dot alpha, you can think of it as g of alpha. G is a function that sends alpha to g of alpha. If g acts on omega, then we say that omega is a g set. That's just the way sometimes people will talk about it. If you hear that, you know that the group G is acting on omega actions. Let's see some examples. A symmetric group. The group Sn, that's all the one-to-one onto maps from n elements to n elements, or you can think of it as permutations of n things. It has n factorial elements. This guy has a natural action on the set 1 through n. In fact, that's how we have defined it. For example, if sigma is in Sn, then sigma is a bijection. How to define sigma dot I? What does it do? Well, it's sigma of I. Sigma is a function. It's sending I to another one of the elements 1 through n, and that's going to be our action. And that satisfies the conditions for an action. The identity element is exactly the element that doesn't move anything. And if you apply one permutation then another, that's actually the way we define the product of a permutation. The product of permutation is the thing that does one then the other. So the conditions for an action are automatically satisfied. And that's why we call it the natural action. For example, S4 acts on 1, 2, 3, 4. Here's an element of S4, 1, 3, 4. That's 1 goes to 3, 3 goes to 4, 4 goes to 1. It's a 3 cycle. And I equals 3 is one of the set elements. What does G do to I? G takes I 3 and sends it to 4. So G dot I is 4. And I can ask you, what's G dot 4? And the answer is 1. What's G dot 1? It's 3. What's G dot 2? 2. Exactly what you might think. G is sending 1 to 3, 3 to 4, and keeping 2 fixed. You're thinking of G as the group S4 in your hand and the set 1, 2, 3, 4 on the ground, and you throw G at it, and what happens? These set elements move around. 1 goes to 3, 3 goes to 4, 4 goes to 1, and 2 stays put. If you had a different element, H being 1, 2, 4, 3, this is the 4 cycle 1, 2, 4, 3. If you throw that across the set, then you get things move around in a different way. You get a different permutation. 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes to 1. Even the visual ways of thinking about it is exactly the way we have been thinking about Sn. So there's not anything new we're saying. In some sense, we're generalizing this idea of the way Sn works with 1 through n, and we want to see that happening with other groups as well. This action of Sn on 1 through n can be extended. Take GBS4, but this time I'm not going to take my set to be 1, 2, 3, 4. I take my set omega to be all subsets of size 2 of 1, 2, 3, 4. So 1, 2, 1, 3, 2, 3, 1, 4, 2, 4, 3, 4. 1, 2, 3, 4 has 6 subsets of size 2, and that's my omega. I'm going to tell you that G acts on this collection of subsets, this family of subsets as well. How does it do that? How does sigma, an element of the group, act on AB? Well, sigma dot AB is going to be what you get when you apply sigma to A and sigma to B. Sigma is a permutation of 1, 2, 3, 4, so you can apply it to A and B. Here are those 6 elements, 1, 2, 1, 3, 2, 3, 1, 4, 2, 4, 3, 4. This time, the set on the ground is these 6 things. It's not 1, 2, 3, 4, but these guys. And I need a group element, for example, 1, 2, 4. What happens to 1, 2? Well, 1 becomes a 2, 2 becomes a 4. So 1, 2 becomes 2, 4. So 1, 2, G moves it over to where 2, 4 was. But what does it do to 2, 4? Well, 2 becomes 4 and 4 becomes 1. And so 2, 4 is going to 1, 4 and 1, 4 is going to 1, 2. So G is giving us a 3 cycle. But what about 1, 3, 2, 3 and 3, 4? 1, 3 becomes 2, 3 because 1 becomes 2 and 3 doesn't change. 2, 3 becomes 3, 4. 3, 4 becomes 1, 3, and G is giving us a different 3 cycle on those other 3 things. This is how G is acting. If you throw G as that set, this is what happens. You get those 3 guys permuting and these other 3 guys permuting. You could have the element 2, 3. What does that do? What does it do to 1, 2? It sends it to 1, 3 because 2 becomes 3. And then what does it do to 1, 3? It goes back to 1, 2 because 3 becomes 2. So H is just switching those 2 guys. And it doesn't do anything to 2, 3 because 2 becomes 3, 3 becomes 2. And 3, 4 goes to 2, 4. 2, 4 goes back to 3, 4, and 1, 4, nothing happens. So this guy 2, 3 switches 2 elements, 1, 2, and 1, 3, switches another 2 element and keeps the other guys fixed. Now let's look at D8, the symmetries of a square. Omega, I'm going to have to be the corners of a square. I'm going to call them 1, 2, 3, 4. A square has 4 corners. And so here's a square, and I've labeled the corners 1, 2, 3, 4. And G acts on omega. Every element of D8 is a symmetry of the square, and each one of them will move the corners of the square. There is a whole video on D8. These symmetries are R0, doing nothing, 90 degree rotation counterclockwise, R180, 180 degrees rotation counterclockwise, R270, 270 degrees counterclockwise, H, a horizontal reflection, a reflection about a horizontal axis of symmetry right in the middle, V, a vertical reflection about an axis of symmetry in the middle going up and down, a vertical one, D is the diagonal that flips about the diagonal that goes to 1 and 3, and D prime is the one that flips about the diagonal that goes through 2 and 4. Here's my set elements on the floor, 1, 2, 3, 4. What does a typical element do? For example, what does R90 do? It does what you expected. It takes 1 to 2, 2 to 3, 3 to 4, 4 to 1, because if you apply R90 to the square, this is what you get. In general, you have to tell me what the action is. It's not like some God-given thing that the action has to be this or that. But in these natural cases, with the way we define D8, and if you look at the video on D8, or the way we define the symmetric group, the action just sort of presents itself, and that's why we call those guys natural action. If I had another element B equals H, all that does is switch 1 and 4 and switch 2 and 3. And so that's the way it's moving the elements of set around. Let me give you a different action of D8. D8 still symmetries of a square. And this time I'm going to say that the omega is going to be the diagonals of the square, the two diagonals. One of them I'm going to call D1, one of them D2. G acts on omega as well, because when you do a symmetry, the diagonals go to diagonals. The identity doesn't do anything to diagonals. And if you do one thing and then another, that's the same as doing the product of the two. The axioms of an action are satisfied. D8 is the same group. In the set, I only have D1 and D2. And what does R90 do? If you do a 90-degree rotation counterclockwise, the two diagonals are switched. D1 goes to D2 and D2 goes to D1. What about a horizontal flip? If you horizontally flip the square, again, D1 goes to D2 and D2 goes to D1. So you get the same thing. A and B in this action act the same way. If you take D, which is one of the diagonal ones, if you flip by the diagonal, if you fix the two corners, the top left corner and the bottom right corner, and flip the square about that, then the blue diagonal stays on the blue diagonal and the red diagonal stays on the red diagonal. And so the action of D is to fix D1 and D2. The purpose of the last example to show that even though every group element is a permutation, it doesn't have to be the two different group elements give you two different permutations. They could give you the same permutation. But we never proved that we actually get a permutation. That's what we need to do now. We have a group, we have a set. If G acts on omega, then G dot alpha is an element of omega for all G and alpha in omega. E dot alpha is alpha. H dot G dot alpha is HD dot alpha. So this was our definition. But what we want to show is that this actually results in a permutation for every group element. G is a group, omega is set, assume that G acts on omega, and then for any group element, define a map that I'm going to show. It's a permutation. I could just call it G and think of G as a function, but just to be super clear, I'm going to give it a new name. So sigma sub G is going to be the function on omega that you get from the action of little g on omega. How is it defined? What does sigma of G do to a set element alpha? It sends it to G dot alpha. Alpha goes to G dot alpha. Then our claim is that sigma sub G is a permutation of omega. If the size of omega, absolute value of a set means the size of omega is n, and that's less than infinity, then sigma of G will be an element of Sn, the symmetric group, because permutations of n things are elements of the symmetric group. I'm not saying anything really that profound. The only thing that I'm saying that needs a proof is that why is it that from those axioms of an action, these two little axioms that didn't seem to be that profound, how do I get that I've got actually a permutation? Let's prove that. So again, we've got a group, a set. The group acts on a set, and we're fixing one element and looking at the map that one element is creating on omega by acting on it. And I want to show that it's a bijection. What do I have to prove? I have to first decide if this guy is one-to-one. Could it possibly send two elements of omega to the same place? Assume that it does. Assume that sigma G sends alpha and beta to the same place. I want to convince you that alpha and beta must be the same. What does it mean to say sigma G of alpha is sigma G of beta? It means when you apply G to alpha and beta, you get the same thing. So G dot alpha and G dot beta, which are the effect of the action of G on alpha and beta, must be the same. But if that's the case, I can look at G inverse dot G dot alpha. And because G dot alpha is the same as G dot beta, G inverse dot G dot alpha should be the same as G inverse dot G dot beta. But now I use one of the properties of the action, which says that if you do two of them in a row, then you can instead take a shortcut and use the product. And so instead of G inverse dot G dot alpha, I have G inverse G dot alpha. And instead of G inverse dot G dot beta, I have G inverse G dot beta. But G inverse G is identity of the group, and identity, the way that acts on alpha, again, one of the conditions of an action is that it gives us alpha equals beta. I started out with assuming that sigma G sends alpha and beta to the same place. I ended up by proving that alpha and beta are the same. So this proves that sigma of G is 1-to-1. What about ontoness? I pick an element in omega and G is going to send some element to beta. I'm going to tell you what that element is. I'm going to tell you what is this alpha that's going to end up at beta. I can't just say it's alpha and G dot alpha is beta because I don't know what G does. But I'm going to tell you what alpha should be so that when I apply G to it, I get beta. So the alpha that I pick, not surprisingly, is G inverse dot beta. G inverse is a group element and it does something to beta. And so G inverse dot beta is some element of the set. Alpha is going to be that. If you don't believe me, how do we check that? The proof of the pudding is in the eating. You just apply G to alpha and see if you get beta or not. G dot alpha is the same as G dot G inverse dot beta. G dot G inverse is the same as G inverse dot beta. This is one of the properties of an action. G inverse is identity, and identity times beta is beta. I started with picking some beta in omega, and I showed that sigma G of alpha is beta because sigma G of alpha is G dot alpha, and that's beta. So the map is 1-to-1 and onto, and it's a bijection. So when you have a group acting on a set, then the function that you get is a bijection. And that's true even if the set is infinite. It doesn't have to be finite. If it's finite, then that means that you find an element of the symmetric group. Another example, GL2R is 2x2 invertible matrices with entries in real numbers. 2x2 matrices, real entries, but not all of them, all of the ones that are invertible. And the group operation is matrix multiplication. What is it going to act on? What's my omega? My omega is going to be R2, the plane. And I'm going to write every element of omega as a column vector. If you pick a group element, A, that's a matrix, a 2x2 invertible matrix, and X, which is a column vector, element of R2, then I define a dot X is just AX, matrix multiplication. Take a 2x2 matrix, multiply it by a column vector, you get another column vector. You start with an element of R2, you get another element of R2. This is an action. Why is it an action? Because the identity element, which is the identity of this group, when you multiply it by X, you get X, as you're supposed to. And if you do A dot B dot X, then that means you're doing A dot BX, and that means you're doing A times BX, and matrix multiplication is associative. So this is AB times X, and AB times X is AB dot X. I just proved to you the two conditions for an action. So what does this mean now? It means that every element of GL2R, every invertible 2x2 matrix, when you multiply it by element of R2, you're getting a bijection from R2 to R2. In fact, from linear algebra, you know that you get more than that. Not only you get a bijection, that's the thing we got now, but you also get a linear transformation. Therefore, every element of GL2R is giving you an isomorphism or automorphism from R2 to itself. I want to go a little bit further and say a little bit more, add another layer of abstraction, but I think this is helpful. Assume the group G acts on a set omega and define, just like we did, sigma sub G, which for some particular G in G is a map from omega to omega. It's defined as sigma G of alpha is G dot alpha. Again, G is an element of G, the group. For all group elements, this sigma G is an element of the permutation of omega. This is what we proved. I've got my group, I've got my set. Every element of the group gives me a permutation. But then that means that I really can think of this as a function from my group to the group of permutations. For every group element, I have a permutation. So I'm going to give that a name. I'm going to define this new map that takes a group element and gives me what? Sigma G, gives me that permutation on omega. Theta of G is just sigma sub G. This thing that G does, now I've given you a number of different names for it. I called it sigma G. Sigma G is the function on omega. Now I've got this map theta that for each G is giving you that sigma G. And my claim is that this is a group homomorphism. What does a group homomorphism mean? It's a map that preserves the operation. A group homomorphism is a function from one group to another, and it has to satisfy this property. That theta of GH should be theta of G times theta of H. Regardless of what G and H you pick, perm omega is a group, G is a group, and I have a function between them. What this says is that the way you multiply things in G is the same as the way you multiply things in perm omega. The corresponding things multiply the same way. If if this group element goes to this group element, this group element goes to that group element, then the product of these goes to the product of those. To prove this, fix G and H in G, because I want to show this for all of them. I'm going to pick two specific ones and see that it works for them. Theta of GH, what is that? Theta of G is sigma G. Theta of H is sigma H. What's theta of GH? It's sigma GH. Sigma sub GH is a function on omega. The other guys, both are functions. How do I multiply them? In the group perm omega, the operation is function composition. By composing sigma G and sigma of H, I have another function. So I have a function on the left-hand side, sigma sub GH, a function on the right-hand side, sigma G of sigma of H, and I want to show they're the same. How do I prove the two functions are the same? I apply them to the domain elements and see that if they give me the same thing or not. So I pick an alpha and omega, and I have to show you that if I take sigma GH applied to alpha is the same as applying sigma G times sigma H and applying that to alpha. I haven't really done the proof yet, but what I've done is given you the structure of the proof. I've planned the proof. I've said this is what I want to prove and this is my strategy. Now I'm going to actually do the proof. The thing you should do is stop the video and do the rest of the proof yourself. In fact, you should do that all the time. Anytime that I claim something, you should stop the video, do it yourself, and then maybe check whether or not I was doing it the same way or not. You might have a different proper way of doing it. Let's start with this sigma GH. Sigma GH is the function that you get on omega by throwing GH at it. And we want to see where alpha is going. By definition, that's the same as GH acting on alpha. We're peeling away these levels of notation. Sigma GH applied to alpha is the same as GH dot alpha. But because this is an action, that means that's G dot H dot alpha. Now, H dot alpha is sigma H applied to alpha, and G dot that means sigma G applied to that. But as I said before, in the group permutations of a set, the operation is function composition. When you have one-to-one onto maps and you want to multiply them, the way we have defined it is that you do function composition. So sigma G of sigma H of alpha is the same as applying sigma G sigma H to alpha, and that's exactly what I wanted to prove. I'm done with the proof that this is a group homomorphism. I want to make a note that I don't really need to make. If A was the identity of the group, then sigma E, theta of E, is identity. If you throw E at the set, nothing happens. That's the identity permutation, the one that doesn't do anything. But then that means that if I take sigma sub G and sigma sub G inverse, G and G inverse are the inverses of each other in the group, then by the thing we proved, which is that sigma GH is the same as sigma G times sigma H, what that tells me is that I get sigma E. But sigma E is identity. So sigma G and sigma G inverse are inverses of each other are invertible. Among other things, that tells me that this is one-to-one and onto, because a function is invertible if and only if it's one-to-one and onto. This is a different proof that the group elements, when they act, give you a permutation. The way this proof goes is that you start by showing that sigma GH is sigma G times sigma H whenever you have a group action. From that, it follows that you have a group homomorphism, but it also follows that each sigma G is a one-to-one onto map is a permutation. This does it in a slicker way than the one I did before. Assume a group acts on a set omega. There are going to be some elements that do not move anything, like identity. Those elements are called the kernel of the action. The kernel of the action is those elements of G that fix every element of omega. The picture that you should be thinking of is this. Whenever you have a group acting on a set omega, you have the map from G into permutations of omega. But it's not going to give you every permutation of omega. Permutation of omega might be huge, but the action gives you some of them. G gets mapped onto the image of that, theta of G. And the kernel are all the stuff that gets mapped to the identity. Later on, when we talk about homomorphisms, we will talk about the kernel and image. The image is going to be a subgroup of permutations of omega, and the kernel is a subgroup of G. In fact, it's a special kind of a subgroup called the normal subgroup. That will be the subject of later videos on homomorphisms and normal subgroups. For now, we don't really need to know any of those, but we do know that given an action, we always have this homomorphism. We have this function theta that's not just a function. For every group element gives us a permutation, but it's a homomorphism. So that means that the way elements of G multiply is the same as the way the permutations multiply over there. Let's look at some examples of this homomorphism and what that tells us. We saw that D8 acts on the corners of the square 1, 2, 3, 4. That meant that each one of these guys gave us a permutation of 4 things, and these are the ones that it gives us. R90 is sending 1 to 2, 2 to 3, 3 to 4, 4 to 1. H is 1, 4, 2, 3, and so forth. It's not just that every one of them is a permutation, but the totality is homomorphism. But it's more than that. It's not onto, because S4 has 24 elements, but we got only 8 of these here, but it is 1-to-1. But a map, it's always onto the image. And the image is a subgroup. The fact that it's a homomorphism means that if you multiply 2 of those permutations, they multiply just like the elements of D8. For example, R90 times R180 is R270. Then this permutation times that permutation is this permutation. Therefore, it's closed. You have inverses, there's identity, so it's a subgroup. This is a subgroup of S4 where the product is exactly the same as D8. So that means that it's isomorphic to D8. This group of 8 elements of S4 forms a subgroup of S4 that's isomorphic to D8. The point is that by having the action, we proved that we hardly any calculation. We had an action. The action gave us a homomorphism from D8 to S4. That homomorphism we see is 1-to-1. And so it's 1-to-1 and onto the image. That image is a subgroup of S4. We have a 1-to-1 onto homomorphism, and that's what an isomorphism is, from D8 to this group. So this group is isomorphic to D8 and is a subgroup of S4. So S4 has a subgroup isomorphic to D8. This was actually a subject of a previous video. In that video, I just alluded to the fact that this is a subgroup isomorphic to D8 and said that we can just go one by one and check. You had to check a lot of different things. But here, I don't have to do that. I have proved to you that S4 has a subgroup isomorphic to D8. And this we get by the group acting. When the group acts, things are revealed. Here, the thing that was revealed is that you can find a copy of D8 inside S4. The other example we saw, the group D8 acted on the diagonals. This is actually even more interesting than the previous example. Here's the diagonals, and here's what everything did. There's not that many permutations of D1 and D2. You can either keep them fixed or flip them. That's all. We saw that a number of different things act the same way. The map, it's not 1-to-1. R0, R180, D and D prime all give us the identity map, whereas R90, R270, H and V all give us, instead of switch D1 and D2, I say switch 1 and 2, the first diagonal and the second diagonal. Now, 1 and 1, 2 is a subgroup of S4. It's a subgroup of order 2. What we call this is not an isomorphic copy of D8, but it's a homomorphic image of D8. It's an image of a homomorphism from D8 into S4, and so it's called a homomorphic image. But does this tell us anything about D8? The other one, when we had that 1-to-1 map that came from an action, we got a copy of D8 in S4, and we were happy about that. But does this tell us anything? And the answer is yes, and it tells us something actually more interesting. It reveals something about D8. This is the map that we have. This is a map from D8 to S4. Doesn't seem that interesting though, but it's a homomorphism. Here's the multiplication table of D8. And so what? I'm going to color blue the elements that go to identity, and I color red the elements that go to 1, 2. And if I do that, here's the blue elements in the multiplication table, here's the red elements in the multiplication table, and it's not clear that I've got anything. Here's those elements again. But what I'm going to do now is I'm going to write the multiplication table differently. Instead of writing it in the order that I had, I will write down all the elements that went to 1 first, then the elements that went to 1, 2. Color them blue and red, but I've reordered them. This is sort of a natural order. I wrote R0, R180, then D and D prime, then R90, R270, H and V. This is not something you would just do because this doesn't seem like a reasonable way. This is the multiplication table. You can write it in any order you want, but this doesn't seem like a nice way of doing it. But if you add the colors in, if you add the blue and the red, we see something remarkable. We see that blue times blue is blue, blue times red is always red, red times blue is always red, and red times red is always blue. What does this remind us of? This reminds us of a multiplication table. In fact, the multiplication table for Z mod 2Z with addition mod 2. You have a group of 2 things, 0 and 1. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. And if you take a bird's eye view of this multiplication table of D8 and go really back, that's all you see. You see blue, red, red, blue. And that's a group. In fact, that's the same group as the subgroup of S4, 1 and 1, 2. That's the same group, the cyclic group of order 2. What we see is that these subsets of D8, we can take them as elements of a group and make a group out of them. You can always do this when you have homomorphic images. we will talk about this in much more detail when we talk about quotient groups. Well, it's the take-home message. Groups reveal themselves. They tell you a lot when they act. If they're just sitting on a corner doing nothing, it's hard to deal with them. You've got to look at their elements. You can look at subgroups, and that's very helpful. But when they act, you can't help it but get to know them. We will see in future lectures all kinds of different ways of gaining information from a group action. What we have seen in this lecture is that you always get a homomorphism from G to the group of permutations on omega. In the case where this omega is a finite set, then you get a homomorphism from G to Sn. If that map happens to be one-to-one, then you get an isomorphic copy of your group as a subgroup of permutations of omega. And even if it's not, you can still get information in some sense. And this will become clear when we talk about homomorphisms, normal subgroups, and quotient groups. That's the end of this talk. There's a whole bunch of talks on group actions coming up, and I will see you at the next lecture.